Hello, welcome to 3.7, Inverses of Functions. Inverse of a relation, we'll talk about that first. Let R be a relation. The inverse of R, and we note that with R with a little -1 up here, does not mean 1 over R. It means the inverse. It undoes what the relation did. It's a set, R inverse goes from B to A, where A sent you to B in the relation. So in the inverse function, B will send you to A. It goes the reverse process. So find and graph the inverse of the following relations. So S inverse here is going to be, well, -3 took you to -3, so this -3 takes you to that -3. -1 took you to -1, so this -1 takes you to that -1. 0 took you to 1, so that means that 1 will take you to 0. 4 takes you to 4, so that 4 takes you to that 4. So let's see, we have -3, -3, -1, -1. Now it's 1, 0, and then 4, 4. I'm going to go to the next one. Now we have a graph y equals the absolute value of x plus 2. Might be helpful to graph this one. Let's graph the original x and y. So if x is -3, y would be the absolute value of -3 plus 2, which is 5. We have -1. Absolute value of -1 plus 2 is 3. For 0, absolute value of 0 plus 2 is 2. For 1, absolute value of 1 plus 2 is 3. And for 3, the absolute value of 3 plus 2 is 5. So for the original function, it's going to be here. 1 was 3. 3 was 5. So this is the graph of y. Now, if we're going to look at x and then y inverse. So in the inverse function, we can switch these, meaning that 5 for x gives us -3 for y. 3 for x gives us -1 for the y. 2 for x gives us 0 for the y. 3 for x gives us 1 for the y, and 5 for x gives us 3 for the y. And you may recognize right off this is not going to be a function because you have 5 gives you -3, 5 gives you 3, 3 gives you -1, 3 gives you 1. So I'm going to change colors for this graph. Maybe we'll go to orange. See how well it turns out. So we have 0, 2, 0. Then we have 3, -1, and 3, 1. And then we have 5, 3, and 5, -3. There. So this is the graph of y inverse here. This is the y inverse graph. This is the original function graph. Now, if the original function, that is a function, vertical line test, the inverse is not a function. So in this, I want to point out that the domain of the original relation of R, the original relation, is the range of R inverse. And the range of R is the domain of R inverse. And I really want to point that out and stress that here. Here's our domain. That became the range over there. Here's our range of the original. That becomes the domain of the inverse. So question, what is the inverse to a relation, a function? More specifically, we may ask, when is the inverse to a function f, written f inverse, also a function? So note that f inverse has already been defined. F inverse stands for the inverse of the function f. So it'll undo whatever f did. If f was x squared, f inverse is the square root of x. Where we are making the use of the fact that a function is also a relation. So remember, all functions are relations. So assuming f is a function, let me scroll this up a little bit, a lot. Assuming f is a function, f inverse will only be a function, and we look at this last case, if it passes the vertical line test. And we see that the inverse here was not a function because it did not pass the vertical line test, which in non-graphical terms means that each element of the domain of f inverse is paired with exactly one element of the range of f inverse. And we didn't have that in this case. Note that the domain of f inverse is the range of f, and the range of f inverse is the domain of f. So when we have the definition of a function being the relation in which each element of the domain is paired with exactly one element of the range, for its inverse to be a function, each element in the range of the original, which is the domain of the inverse, must be paired with exactly one element of the, I should say here, range. This is domain of inverse. The range, meaning the domain of the inverse, must be paired with exactly one element in the domain, which is the range of the inverse. And this brings us to the concept of a one-to-one function. Now, one-to-one means a function f is one-to-one if for every pair of distinct elements x1 and x2 in the domain of f, we have f of x1 is not equal to f of x2. That means for every element of the range of f is paired with exactly one element of the domain. So, in a one-to-one, every x has just one y, every y has just one x. That's one-to-one. So each thing has exactly one partner. You can't have 2 going to 5, 3 going to 5, 4 going to 5. That would not be one-to-one. You only have one. Your y can only have one thing in the x's. This property can be illustrated vertically, or I should say visually, not vertically, visually, or graphically, using the horizontal line test. So the way this works, if you can draw a horizontal line and it hits more than one time, it's not a one-to-one. So here we're hitting more than one time, this is not one-to-one. Over here, this hits only one time, so this is one-to-one. The horizontal line test. Let f be a function. We say that the graph of f passes the horizontal line test if every horizontal line in the plane intersects the graph no more than once. Here, only one time. This is one-to-one. This crossed twice in many places. So this is not one-to-one. So we're going to do or determine which of the following functions have inverses. So if they have inverses or not, if not, suggest a domain to which the function should be restricted so it'll have an inverse. The first case, g of x equals x minus 2 cubed minus 1. And we recognize this, hopefully, as a cubic function. Cubic has this kind of a curve, but it's shifted to the right 2, is that 2? And it's down 1. So we'll go 1, 2 that way, down here. So they come up, cross there, and go up. This is one-to-one. Horizontal lines, I'm going to hit it one time. Now the next one, however, because the negative's out in front, this is reflected across the x-axis, and the 5 means, the plus 5 means it's shifted up. So if we looked at that as a graph, it's going to be coming up here, like that. So this is not one-to-one. But we can restrict the domain. We can cut out the part that mirrors it, which is right there. We can cut that off. And if we say, okay, look at this graph from 0 to infinity. Let's do this. Now this is one-to-one. You could also have restricted it from negative infinity to 0. We tend to like to keep things positive. It's, I don't know, like a math thing. And then p of x equals 10 minus x. So again, this could be written as negative x, 10 minus x squared, negative x squared plus 10. So it's like what we just saw above. And if we restrict that domain from 0 to infinity, this is one-to-one. So the idea here, this one's one-to-one because it only hits one time. The horizontal line would hit more than one time in these cases, so if we restrict it from 0 to infinity in both these cases, it is one-to-one. I'm going to go on to page 3 here. To find a formula for F inverse, this is kind of fun. Let F be a one-to-one function and assume that F is defined to be a formula. To find a formula for F inverse, perform the following steps. You replace f of x with y, and you get an equation with x and y. Okay, interchange the x and y, solve for y, replace y with f inverse of x. So here we'll say y equals 4x minus 3. We'll swap the x and y. X equals 4y minus 3. Solve for y. So x equals 4y minus 3. We'll add 3 to both sides. X plus 3 equals 4y. Divide by 4. Y equals x plus 3 over 4, or f inverse of x is x plus 3 over 4. Oh, this is g, excuse me. G inverse. For the next one, y equals 1 minus x over 1 plus x. Swap them. X equals 1 minus y over 1 plus y. And a problem like this tends to bring a little bit of anxiety for students. I understand that. And it can be a little tedious. So we're going to go through this process. We have x equals 1 minus y over 1 plus y. And the idea is to clear the denominator. So if I multiply by 1 plus y, I would have x plus xy equals 1 minus y. And the idea is to get the x's, which are the y terms on one side, non-y terms on the other side. So if I add y to both sides, I have x plus xy plus y equals 1. And subtract the x, I have xy plus y equals 1 minus x. You can factor out a y. Y times x plus 1 equals 1 minus x. And divided by x plus 1, y equals 1 minus x over, and you can call that 1 plus x. So this was an s. S inverse of x is 1 minus x over 1 plus x. So I'll give you 5 seconds to figure out what is interesting about this answer. Okay, if you said what's interesting is, check it out, this is the same thing as what we started with. So meaning this one is its own inverse. This function is its own inverse. Kind of cool, I think. Well, that's the basic process for this. Is you're going to swap them, multiply. Trying to solve for y, you want to clear the denominator. You distribute. You get your y's on one side, x's on the other side. You factor out the y, divide, and there you go. Let's go to C. We have y equals x cubed plus 1 to the 1/5. Swap them. So x equals y cubed plus 1 to the 1/5. Now I want to solve for y, so I've got to undo this 1/5. So it'll be x to the 5th power equals y cubed plus 1 to the 1/5 being raised to the 5th power. So x to the 5th equals y cubed plus 1. Then we'll subtract the 1 from both sides. X to the 5th minus 1 equals y cubed. And what do you think we do next? We're solving for y, so how do we get this power away? Very good. We take the cube root of both sides. So y equals the cube root of x to the 5th minus 1. Or, this was a inverse of x equals the cube root of x to the 5th minus 1. Okay, so last thing here from this page, properties of inverses. F of f inverse of x is x for all x in the domain of f inverse, and this is the range of f. And f inverse of f of x is x for all x in the domain of f, which would of course be the range of f inverse. Okay, let's go to the next page. Says, in each of the following problems, show that f of f inverse of x equals x. And when you have this case, f of f inverse is just x as we just discussed. It'll undo it. If you do the inverse of a function doing composite, you get that number back, the x back. So we're going to show that f inverse of x, f of f inverse of x equals x, and f inverse of f of x equals x. So here we're going to go. F of f inverse of x, that's going to be f of this amount, x plus 1 cubed minus 2. So this x plus 1 cubed minus 2 is going to go in place of this x. That's the cube root of x plus 1 cubed minus 2, and then there's a plus 2, and then outside that there's a minus 1. So these 2's subtract out, and we're left with x plus 1 cubed minus 1. That's just going to be x plus 1 minus 1, which is x. That worked. Then f inverse of f of x is going to be x plus 1, no, I'm sorry, f inverse of the cube root of x plus 2 minus 1. So this, all this is going to go in place of that x. It's going to be the cube root of x plus 1 minus, sorry, getting this mixed up, x plus 2 minus 1. Then we have a plus 1 here. This plus 1 is right here. We're cubing that, and then minus 2. This minus 2. So this part right here is my f of x. That's the f of x. So we have the cube root of x plus 2, the minus 1 plus 1 subtract out. This is cube minus 2. The cube root of something cubed is going to cancel, so it's x plus 2 minus 2, which is x. It works out as well. That's kind of cool. The next one, f of x equals x squared. F inverse of x is square root of x. So f of f inverse of x is f of the square root of x. So we have the square root of x squared. That's just x. And f inverse of f of x is f inverse of x squared, which is the square root of x squared, because our f inverse is square root. That's x. Now what's important to remember here is this: they restrict the domain to being just the positive values of x. So our graph of the original function looks like this, and the graph of the inverse function looks like this. Okay, I'm going to go on to the next one. Okay, we have f of x equals x minus 5 over 2x plus 3. F inverse is 3x plus 5 over 1 minus 2x. So this is going to have some complex fractions in it, which may be a little uncomfortable for some people, but we have to kind of push ourselves there. So f of x is going to be f of 3x plus 5 over 1 minus 2x. So that means this expression goes in place of the x in the numerator and the x in the denominator. This is going to be our 3x plus 5 over 1 minus 2x minus 5 over 2 times 3x plus 5 over 1 minus 2x plus 3. Okay, I'm going to go ahead and multiply everything by the 1 minus 2x. To clear out that denominator. So that's just going to give us 3x plus 5 minus 5 times 1 minus 2x. So 1 minus 2x here, that just cancels, gives us 3x plus 5. And we have our minus 5 times 1 minus 2x over, doing the same thing here, these are going to cancel. I have 2 times 3x plus 5, that's 6x plus 10 plus 3. Okay, that's going to be 3x plus 5 minus 5 plus 2x over, I'm missing something. Oh, I didn't distribute this. 3x times 1 is 3. 3x times negative 2 is negative 6x. Down below we have the 6x's cancel. Maybe I should do this in more steps. Do 1 minus 2x. Okay. So 6x plus 10 plus 3 minus 6x. This should be a 10x here, shouldn't it? There we go. Now on top, we have 3x plus 10x is 13x, where these 5s will subtract out. Down below, the 6x's subtract out, and we're left with 13. That leaves us with just x. So that one worked. In the second case, we're going to be putting this x minus 5 over 2x plus 3 in place of the x up here and down there. Back up here. So it's going to be 3 times x minus 5 over 2x plus 3. Plus the 5. So let's see that 3 times the x over 1 minus 2 times x minus 5 over 2x plus 3. So we will have, I'm going to again multiply by the common denominator, 1 over, 2x plus 3 over 1 over 2x plus 3 over 1. So in the first case, that's just going to cancel here. You have 3 times the x minus 5. So 3x minus 15 plus 5 times 2x plus 3. Down below, you're going to have 1 times 2x plus 3 minus 2x. 2 times negative 2 times negative 5 is plus 10. So we have 3x minus 15 plus 10x plus 15 over 2x's go away. We have 13 down below. So up on top, 15's go away. It's 13x over 13, which is equal to x. That worked. Yay! Okay, consider the graph of a function f and the graph of its inverse. How do they compare? The graph of f inverse, the inverse of the function of f, is the graph of f reflected across the line y equals x. So this means that if, as we saw earlier, here's your x squared, here's your square root of x, it's reflected across this line, y equals x, reflected across that line. So the last page here, showing you with the TI-89, we're doing x cubed next to 1/3, x cubed x to 1/3. Now this looks a little jumbled, and I try to get the spacing to be consistent. But here's y equals x, here's x cubed, here's x to 1/3. So this point is reflected across there, 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 and inside that. So the graph of f inverse is the graph of f reflected across the line y equals x. So here's y equals x. This is y equals x to the 1/3. This is y equals x cubed. Okay. And that'll do it then for section 3.7. I hope you enjoyed that. I hope you enjoyed chapter 3 and some of your questions. Thank you.